This meeting is being recorded.
Okay, good afternoon. Screen is visible.
Yes, sir.
Okay, so in last lecture, we have discussed the central idea of this subject, CMOS VLSI design, right? Then COs, course objectives, course outcomes. Okay, what are different practicals that we are going to perform for this course or subject, right? So, and along with the overall central idea, its prerequisite and all. Okay, so we have discussed the central idea of this subject. Also, we have discussed syllabus also, examination scheme, then credit scheme, everything we have discussed. So in this lecture, we will actually start with the unit number first, that is MOS transistor theory. Okay, so what are different points that we are going to cover in this unit? Physical structure of MOS transistor, its accumulation, depletion and inversion modes, MOS device design equations, right? That includes different uh, VD, ID, right? Based on the VI characteristics, you can have the current and voltage equations for the MOS transistor, as you have studied for the BJT, right? So for the BJT, you have different uh, equations, VC for the VB, right? VE, then IC, IE, IB. So all that nomenclature you well aware of. So in similarly, in case of MOS transistor also, we have some terminologies, right? VD, it's a drain voltage. ID, it's a drain current. So all these are going, we are going to discuss in this design equation. Then second order effect, technology scaling, static and dynamic behavior of CMOS inverter, power and energy delay, impact of technology scaling on inverter. So these many points we are going to discuss under this unit. Okay, so before start with the uh, actual syllabus, some few points that we should understand to have the better understanding of this subject. Okay, so have a very careful look on this diagram. It's a design abstraction levels in digital design, right? So you are just, or you might aware of only the last system level design, or that you can say it's a IC, integrated circuit. Okay, but uh, do you have, or do you have any curiosity what is inside that IC? That is the question. Okay, okay, if I have given you, say, op-amp IC, right? 741, all of you have studied in your AIC subject, right? Analog integrated circuit, or LIC maybe. So you have studied that 8 pin op-amp IC 741. Okay, so okay, fine, you have just implemented that IC on a breadboard. You have connected some external components, and you might have performed different experiments also. Okay, that you might have did. But have you thought of what could be inside that op-amp IC, right? That black covered IC, right? Having the 8 leads out from it. So what could be inside that? So here, here is the answer for that. So inside that there are different modules or different digital gates. If it's a digital IC, it could be a digital gates. Then uh, that modules or that black box is made up of different gates, right? For example, uh, multiplexer is a module, but that multiplexer can be built by using different NAND and NOR gates. Am I right? Multiplexer is a module, but that multiplexer you can use, or you can build or you can design using different NAND and NOR gate. So again, what is inside that NAND and NOR gate? So transistor, or uh, nowadays you can say it's a MOS transistor or CMOS transistor, right? So you might have studied in your maybe I don't know subject. So have you studied the TTL logic, right? What do you mean by TTL logic? Transistor logic, CMOS logic, right? So what is it? It's actually the circuits or the logic. It's a basic gates that can be used to build that particular gate, or in an abstract level you can say a design, right? So inside that gate you have a number of MOS transistors or CMOS transistor. Now our subject is a CMOS VLSI design, so we will be using CMOS transistors. Okay, but it is possible with the MOS transistor also. Every what we can say, every logic family has certain advantages and disadvantages. So based on your requirement you can go for TTL logic, that is transistor logic. It's a one logic family. Okay, it has some design rules and specifications. If you want to go for say CMOS logic, okay, so it's again one more logic family that you can be used to design your digital system or digital design, right? So based on the requirement and application you can choose that appropriate logic family. You have to abide to that particular rules and specifications, and then you can go for the designing part. Okay, so uh, just a brief difference between the TTL logic and CMOS logic is what? In case of TTL logic, right, the number of transistors that may require to design a particular gates are more as compared to the CMOS. Means, for example, say uh, for the same example you can take for op-amp, right? Op-amp 741 IC. If you could design that IC with the help of TTL logic or based on the TTL logic family, so number of transistors required may be more. If the same IC with the same design you can build with the help of CMOS logic. Means, for example, if in case of CMOS logic family, to build a particular design, if you require say 500 CMOS transistors, right? For the same design you may require 1000 transistors or your normal BJTs. That means what? So CMOS requires almost 50% less number of transistors to build the same design. That is why that is what I want to convey to you. Okay, so remember this figure. This could be a very helpful. Okay, so first you have a system level, then module level, then gate level, circuit level, and device level. Okay, so while in your last semester DDS subject, whatever the VHDL code you are writing, it's a it's a three level design. Okay, it can go to a system module and some part of RTL. But if you consider a Verilog, then it is four level design, right? It up to gate level you can design by using Verilog, not VHDL. VHDL you can design up to three levels only. In case of Verilog you can design up to four levels. So you might have remembered that point. Okay, so this is about the uh, design abstract levels in digital design. So in this course we are going to focus on the device level, as we are using or we are focusing on a CMOS, right? So we have to use this CMOS device and we have to build or we have to design different digital circuits. So mostly in this course we are going to focus onto a circuit and device level. Okay, so now all of you are aware of what is an IC. Okay, what is an IC? Or first, what do you mean by IC? Integrated circuit, right? Integrated circuit, as its name indicates, it's a combination of different modules that modules is made up of different logic gates. That gates itself made up of s- uh, uh, parallel or series combinations of CMOS or uh, MOSFETs or BJT also if you are going for the TTL logic. That is a IC, very simple definition of IC. So an integrated circuit is a small semiconductor based electronic device that consists of fabricated transistors, resistors and capacitors. Okay, that entire thing forms a integrated circuit, right? Which can include different transistors, right? Again, transistor means not always your bipolar transistors. No, it could be a MOSFET, it could be a CMOS. Okay, depending upon which type of logic family you are preferring. It is a TTL or a CMOS or there are many more. Okay, and these integrated circuits are the building blocks of most electronic devices and equipments. Again, need not to talk much on this statement. Although as an electronics engineer, you are aware of this. Okay, everything which is a built of everything which you say it's an electronic device, it must have ICs. It must have some electronic circuits designs. Okay, irrespective of anything. When you say something is electronic equipment or device, it must have ICs. Okay, that is a part and parcel of electronics device. Okay, so what are different technology or the IC technology that has been evolved, okay, since many years back to nowadays. Okay, so there were first only SSI. What do you mean by SSI? Small scale integration. Okay, in year 1960, which consists of less than 100 IC, sorry, less than 100 transistors in a single chip. Okay, then you have a medium scale integration, that is MSI. So in this MSI, the number of transistor range between the 100 to 1000 in a single chip. Then you have a LSI, large scale integration. Okay, see how technology is getting evolved day by day, year by year. Okay, now in case of LSI, you are having 1000 to 10,000 number of transistors it can accumulate on a single chip, that is a LSI. Now after LSI you have a VLSI, very large scale integration. So it has almost 10,000 to 1 lakh number of transistor it can occupy or it can accommodate on a single chip, that is the VLSI. Then you have a ULSI, ultra large scale integration. Again its range increases to 1 lakh, uh, yes, to 1 lakh to almost 10 lakhs or rather more than 10 lakhs. Okay, so sorry, 1 crore, 1 lakh to 1 crore. It's a ultra large scale integration. Okay, then SLSI, super large scale integration. Okay, so it can accommodate more than 1 crore transistor on a single chip. Okay, now you can imagine how technology is getting evolved and updated day by day, year by year. Okay, now you have studied this already in your maybe digital technique subject, second year subject, Moore's law. Okay, what is statement of Moore's law? So number of transistors on a microchip or in a IC doubles every 2 years. Okay, number of transistors that the capacity of IC, occupying capacity of IC in case of transistor doubles every 2 years. So it's a very strong statement made by the scientist Gordon Moores, and up till now it is or we can show that it is valid and it proves or it stands very great importance as far as our electronic field is considered. Okay, we are getting the day by day, year by year, the technology is getting evolved, technology getting innovated, advanced things are coming into the picture. Okay, so we are uh, marching towards the nanotechnology era, right? So maybe in a single chip that may size even a lesser than your nail, right? Even a lesser than your nail can occupy 10 crore transistors, right? It can be possible. Maybe in upcoming 10, 20 years, the nanotechnology will be the uh, prominent, uh, or it can be a very uh, prominent topic of research. Okay, nanotechnology. So this is stating by the Moore's law. Okay, so always remember, its perception is that the number of transistors or a microchip that keep getting doubles after every 2 years. Okay, so this is about the Moore's law. Now, need not to tell about VLSI. So mostly in your third year, first semester subject, you might have studied this, right? In digital design and HDL. What is VLSI? Okay, different HDL languages. So all this part you have already studied. Now coming to the MOSFET. Now what is MOSFET? Metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor is a abbreviation of MOSFET. Okay, so if you quickly compare the MOSFET with your BJT, that is your normal bipolar junction transistor. So what is the difference between BJT and MOSFET? Can anyone? Can anyone able to highlight a difference between BJT and MOSFET? Okay, so BJT stands for bipolar junction transistor. Okay, MOSFET stands for metal oxide semiconductor field effect transistor. Now, all of you know, the as the name indicates, BJT bipolar means what? It's a bipolar device. MOSFET is a unipolar device. Now the question is, what is bipolar and unipolar? So bipolar means what? The current or the overall current is contributed by the minority as well as majority carriers. It's a bipolar device. But in case of MOSFET, as it's a unipolar, the current, the drain current is contributed by only and only majority carriers. Okay, this is the very fundamental difference that you should remember. So BZT is a bipolar device. That means what? Current is contributed by minority as well as majority carriers. And in case unipolar means what? The current is contributed by only majority carriers. There is no current contributions or the current contribution from minority carriers in case of unipolar device, and which is a MOSFET. MOSFET is a unipolar. So coming to the next difference, what you can say, MOSFET is a voltage control device, whereas BJT is a current control device. This can be a major difference. Okay, then in case of BJT, you have a three terminals. In case of MOSFET also, you can have a three terminals, but in some cases you can have that extra fourth bulk terminal also in case of MOSFET. Okay, so these are the major differences that you can remember. Okay, what are the three terminals of MOSFET? So basically it's a source, gate and drain. Okay, source, gate and drain. So can you relate this with the BJT terminals? Can you relate? सांगता येईल का कोणाला?
So collector base emitter.
Okay, that is fine. In case of BJT, collector, base, and emitter. Okay, but in case of or what is analogous to collector in case of MOSFET? That is my question. Can anyone? You can think on it.
So collector,
Hmm.
drain, gate,
Very right. Hmm.
base, and emitter, source.
Very right. Very right. So basically, emitter is a source, right? Gate is equivalent to a base and drain is a collector. Very right. So this analogy you should remember. And one more thing, BZT has a negative temperature coefficient or positive temperature coefficient. So remember, this could be a major difference between these two devices. BZT have a negative temperature coefficient, whereas MOSFET has positive temperature coefficient. Then talking about its impedance, you can say input impedance. BZT have a low input impedance, whereas MOSFET has high input impedance. Talking about its switching frequency, BJT has low switching frequency, whereas MOSFET has high switching frequency. Okay, so basically these are the major points that you can differentiate between this BJT and MOSFET. Okay, now what are different types of MOSFET that we can have? Okay, so basically MOSFET is of two types: enhancement type and depletion type. In again enhancement type, you have a N channel enhancement mode, you have an enhancement mode of P channel, right? Then similarly in case of depletion type also, you have a N channel depletion mode and you have a P channel depletion mode. So this is a classification of the MOSFET devices, or you can say the types of MOSFET. Okay, basically there are two: enhancement type and depletion type. So there is a N channel enhancement type, P channel enhancement type, and similarly in case of depletion type, there is N channel depletion mode and P channel depletion mode. Okay, so the symbol and the actual physical view of the MOSFET is shown in the slide, so you can have a careful look on that. So basically, this is the structural view. Okay, if you have the front view of the cut section of MOSFET, so it's much look like that. So it has a source, it has a gate terminal, and it has a drain terminal. Okay, so in between the drain and source, when you travels from the drain to source, okay, there is a channel formation. Okay, there is a channel formation. This is a structural view of MOSFET, and on the right hand side you can have the physical view of formation. So first terminal is always gate, second is middle one is source, and last one is drain. Okay, so now we will talk about the depletion type mode. Okay, which can be referred as normally on MOSFET. Okay, depletion type MOSFET, which can be referred as normally on MOSFET. Okay, why it is referred as normally? on MOSFET. So basically in this type, the channel is already established, right? In case of depletion type, channel is already established. That means what, how you can evident that? So at zero voltage also, that means you don't provide anything to that depletion MOSFET also, right? You can evident a small current, right? You can evidence a small current that is flowing from that depletion type MOSFET. So that's why it is referred as normally on MOSFET. Okay. Unlike a enhancement type, in case of enhancement type, right, it's normally off MOSFET. Means what? When there is no voltage, there is no current. Okay. In case of depletion at zero voltage also, you can evidence a small amount of current, that you can say quiescent current, okay, flowing through this depletion type MOSFET, and that's why it is referred as normally on MOSFET. Okay. So here the channel is depleted of charge carriers to reduce the width of channel. Okay. To reduce the width of channel, the gate voltage is inversely proportional to the current. Okay. In case of depletion region, gate voltage is inversely proportional to the current. That means as voltage decreases, current increases. Voltage increases, current decreases. There is an inverse relation between the gate voltage and drain current in case of depletion type MOSFET. Okay. You can have the VI characteristics of the depletion type MOSFET as well as enhancement type MOSFET. In case of depletion type, right? So ID at a zero voltage also, there is a some current that you can see here. At zero voltage, there is some value of ID current you are getting in case of depletion type MOSFET. But see, in case of enhancement type, at zero voltage, current is also zero. This is the on x-axis, it's a voltage. On y-axis, it's a current. So here you can say, if you consider this point, definitely you will get some value of ID, and where the voltage is zero on x-axis. But in case of enhancement type, you can see here the current is also zero and voltage is also zero. Okay. So these are the VI characteristics of enhancement type and depletion type MOSFET. Now again, as we have discussed, uh, this depletion type MOSFET, okay, uh, again have two types, N channel and P channel. Okay. N channel depletion type MOSFET and P channel depletion type MOSFET. Okay. So this point we are going to discuss in the next lecture. For today, we will stop here. If you have any query or doubt, you can ask me right now. Everyone understood with this?
Yes, sir.
Okay.